There's this invisible language, this kind of secret grammar that powers almost everything you do online. Seriously, from scrolling your social media feed to that thing you just bought, it's all running on the same logic. So today, we're going to pull back the curtain on that grammar and see what really makes it all tick.
So, have you ever really wondered how databases actually work? I mean, deep down. It's one thing to use them, but it's something else entirely to get the beautiful logical engine that's humming away under the hood. Well, that engine, it speaks a very specific language, and that language is called relational algebra.
Okay, the best way to get your head around this is to think about it like this. You've probably heard of SQL, right? Maybe you've even written some. SQL is the language we speak to the database. It's the practical, hands-on tool. But relational algebra, that's the grammar. It's the fundamental set of rules that makes a language like SQL even possible. It's the theory behind the practice.
So, what is it, really? Well, relational algebra is a formal language where every single operation takes a table, or what's formally called a relation, as its input, and it always spits out a brand new table as its output. And this is the magic part. The key feature here is something called closure. Because the output is always another table, you can just chain operations together. It's like Lego. The output of one piece becomes the input for the next. This lets you build these incredibly powerful, complex questions out of really simple, basic parts.
All right, let's start with the absolute basics. How do we just shape a single table of data? To do that, we're going to look at the two most fundamental tools in the whole toolkit: selection and projection.
First up, we've got selection. You'll see it written with the Greek letter sigma. Just think of this as a horizontal filter, plain and simple. It goes through a table, row by row, and it only keeps the rows that match a condition you set. If you've ever typed where in an SQL query, yep, you've been using selection. It's the exact same idea.
Okay, let's make this concrete. Here's a sample staff table we're going to play with. Pretty straightforward, right? We've got staff number, first name, last name, and salary. A nice, clean little data set.
So, let's put selection to work. Let's say we want to find all staff members who make more than 10,000. We run the operation, sigma, salary more than 10,000 on our staff table, and boom, we get back a brand new table that only has the rows that match our rule. See? It's literally a horizontal slice of the original data.
All right, our second big tool is called projection, and it uses the Greek letter pi. Now, if selection was our horizontal filter, projection is our vertical slicer. This one lets you pick and choose only the columns you care about and just throws away the rest. Oh, and here's a key detail. It automatically gets rid of any duplicate rows for you. And yeah, you guessed it, this is the theory behind the select keyword in SQL. Okay, back to our original staff table. Let's see what happens when we throw a projection at it.
And there it is. We apply the operation pi with the columns we want, staff no, fname, salary, and we get back this new, skinnier table. It's just those three columns. We've literally sliced the data vertically to get only the info we were looking for.
Okay, cool. So we can slice and dice a single table pretty well. But what happens when we need to start working with two tables? Well, this is where some classic ideas from set theory come into play.
Now, for tables that have the same basic shape, same number of columns, and the columns match up, we have three really powerful tools. Union just smushes the rows from both tables together. Set difference is cool. It gives you the rows that are in the first table but not in the second. And intersection, that gives you only the rows that show up in both tables. But here's the catch, and it's a big one. This only works if the tables are union compatible. They gotta match.
But that leads us to probably the single most important question in the entire database world. This is where relational algebra really flexes its muscles. It is time for the art of the join.
Think about it. So far, we've only dealt with tables that look exactly alike. But the real world is messy, right? Data is spread out all over the place. So how in the world do you connect a table of, say, university courses with a totally different table of teaching assistants? Well, the first idea you might have, the most, let's call it brute force approach, is something called the Cartesian product. Just imagine this. You take the very first row from your first table, and you pair it up with every single row from the second table. Then you take the second row from the first table and do it all over again. It is a complete, unfiltered, everything with everything mashup.
And yeah, as you can probably imagine, this gets out of control fast. Our two little tables for course and TA just explode into this giant, messy table that's mostly filled with junk.
Meaningless combinations like pairing a statistics TA with a computer science course. It's just noise. It's not useful.
The math here is actually super simple and kind of terrifying. The number of rows you end up with is just the number of rows in the first table times the number of rows in the second. This combinatorial explosion, as they call it, makes the Cartesian product insanely inefficient. It's almost never what you actually want to do.
And that brings us to the hero of our story, the join. The join is the elegant, smart solution. Here's what it does. It's basically a Cartesian product, but it's immediately followed by a selection. So it does that brute force combine everything step, but then it instantly filters that huge result down, keeping only the rows where there's a meaningful connection, where the data in a related column actually matches up.
And look at this beautiful result. By joining our course and TA tables on that common department column, we get this. A clean, meaningful table that makes perfect sense. We can see exactly which TA is associated with which course in their own department. This is the operation that really ties a whole relational database together.
So we've gone through a handful of key operators now, but the real magic, the absolute core idea of relational algebra, is how these few simple tools can be combined to answer almost any question you could ever dream up. They are the fundamental building blocks for every single data query.
There's actually a formal term for this. It's called being relationally complete. All that means is that a language has enough power in its toolbox to ask any question that it's theoretically possible to ask of the data.
And this is a perfect way to see that building block idea in action. Remember the intersection operator from earlier, the one that finds rows that are in both tables? Well, it turns out you don't even need a special operator for it. You can build it yourself using just set difference. Think about it. The intersection of two tables, R and S, is just everything in R, take away the things that are in R but not in S. It's simple, it's powerful, and it's just so elegant.
And it turns out you can boil this entire language down to just five fundamental operations: selection, projection, union, set difference, and that brute force Cartesian product. Every other operation we've talked about, even the super powerful join and the intersection, can be constructed from some combination of just these five. This is it, the complete minimal toolkit for talking to your data.
So, what we've just done is uncover the basic letters and grammar of data. And this theoretical grammar is the secret to why modern databases are so dang powerful. It's the foundation that lets a database's query optimizer look at your SQL, break it down into these building blocks, and then rearrange them into the fastest possible way to get your answer. So now that you get it, now that you understand the fundamental verbs and nouns for shaping information, what incredibly complex, what really interesting questions can you start to imagine asking your data?